session. All right, so I'm going to wrap up everything that we have done last time about the potential and potential energy using this particular example. All right, and this is under the topic of potential energy. So we sort of like come in full circle right here. So everything just circulate back to the original point. You guys familiar with potential energy based on the experience in gravity? Okay, so it's the same concept. All right, we have already seen the relationship or the comparison between what we are doing with the gravitational field and the electric field. So we already discussed about the concept of potential energy in gravity is the same thing as the concepts of potential energy in electricity. So now we're going to redo that again, but from the light of under the light of potential. You guys remember, right? Remember that in electricity, you have you have two parameter or two quantities here. One is just pure potential, no energy, and the other one is potential energy, right? So those are the two different things, but those two things are related simply by you guys. I hope you guys remember this. It's simply this, right? Because we define the potential to be the energy per unit charge. So the other way that you can think of this one is like V is just U over Q. That's what it is. All right. And another thing that we discussed last time was we saying that, hey, Ajahn, usually we always talk about the potential difference. Yeah. When you say potential difference or the energy between 2 points, let's say. So it's going to be the same scenario as you when you were talking about the gravitational potential energy. Usually you have to say, hey, let's take the ground to be the height of 0. Then when you bring the mass up, you say, hey, if this is a height h, then you say the gravitational potential energy of this mass is mgh. The h that you're using is the height with respect to your reference. And if you remember back in the day that you can choose your reference at any point that you prefer. For example, you can take the top of the building to be height 0, you take the ground to be 0, or you can dig underneath the ground to be 0 height. It doesn't really matter because at the end you are only care about the change. Yeah, just the displacement or just the distance between the initial point to the final point. That's what you care about. So that concept of only care about the difference is going to get carried over to here. Same thing. So usually you don't talk about the potential alone. Usually it's a potential difference. It's between 2 points. However, what we learned last time was like, okay, if we really want to talk about potential at a point, so it means you have to imply some reference point. So we have a word saying that, okay, let's take V at infinity to be 0. Remember that? That is a line, a clause saying that, hey, let's take potential to be 0 at infinity. So once you do that, that allow you to always reference to that point. And that allow you to use this relationship over here when you are trying to calculate potential from a charged particle at a distance r away from it. Sounds cool? All right. So just, I mean, the whole point I want to summarize over here, just to talk to you one more time that, hey, guys, whenever you talk about potential, it's always potential energy, difference or potential difference. It doesn't really matter. It's you have reference at anywhere. You only talk about the difference. Okay. So just to confirm one more time, in your household, when you use your electricity at home, right? Your household electricity is 220 volts. So that's 220 volts. Actually, it's just the difference between those positive and the negative poles of whatever your outlets and all this stuff. That's it. You don't really know which one is at what value, but you only know that the difference between those 2 points is 220 volts. Does that make sense now? All right. So that's the key. The key is you always comparing one point to the other point all the time. And that's what this question is about right here. So if potential at point P can be calculated, right, due to another charge Q1. So you have Q1 on the left, you are standing at point P. So everyone knows how to calculate the potential at point P simply by KQ1 over the distance. Cool. So this one check. Now, if you want to bring in the second charge, so you have another charge Q2. And of course, in the first place, Q2 is not in the picture, but suddenly you somehow you want to place Q2 charge there. So the idea is you're probably going to drag the Q2 charge from somewhere very far away. Does that make sense? So you probably like grab Q2 charge, when you say far away, when you talk about like electrons and proton and all this stuff, 1 meter or maybe 10 meters is already far away. So when you drag a charge, the second charge from so far away, so it's the same thing as you drag it from infinity to point P. Does that make sense? All right. So that means you're trying to go from initial point is at infinity, you drag it to final point to be at point P. So the potential difference is going to be final minus initial. Does that make sense? Okay. So it means the potential at final point is at point P. The potential at the initial point is at infinity. But we already said the potential at infinity is 0. So that's why, I mean, in the first pass of this one, it looks like the potential difference is the same thing as the value of the potential at point P automatically. So that means when you already knew how to calculate the potential at point P, it's pretty much automatically implied that you can think of it, this one is like it's a dragging of a charge from infinity to that point. So how much energy required? Ajahn, easy. The energy is just the charge multiplied by the potential difference. But you just say the potential difference is just the potential at that point. So that's it. You just pop in the Q2, multiply by that expression, you get K, Q1, Q2 over the distance. You are pretty much done. Sounds cool?
Okay.
And that's why I think maybe sometimes you probably have seen the formula back in the day. It might look like this: U equal to K Q1 Q2 over distance between those 2 points. But personally, I don't really like this that much because, well, I prefer to think of the energy to be the energy required for you to move charge from one point to the other point. So it's sort of like it has some changes going on. Okay. But when you look at this formula alone, it's like it's look pretty static. It's like you have two charged particle and you want to calculate the energy of the system. So, but anyway, both are good, both are correct. But to me, it seems like by understanding that when you want to calculate the energy, it's the same thing as you'd have to do some work. It's the work done in dragging the charge Q2 from infinity to that point. So you do something. Yeah. So the idea that you did was just like what you did with the thermodynamic system. Yeah, there is an external force supplying some work, and that work done increase the energy of the system by delta U. So that's kind of nice. So the concept of the thermodynamics that you learned before still apply here. Cool? Okay.
Okay.
ในการพูดรู้เรื่องไหมเนี่ย พอได้ Okay. All right. So let's try this one. Okay. So let's practice one more time. So let's say the question might be asked you something like this. Find the work done in bringing the 4 microcoulomb charge from so far away to point P. So now you've got the concept. Ajahn now is easy. If you really want, all you need to do is just figure out what is the potential at P. Right? If you can figure out the potential at point P, and then you multiply the 4 microcoulomb charge to that potential at that point, it will be the same as the amount of energy that you need to drag the charge from infinity to that point P. Cool? And everyone knows how to calculate the potential at point P now. You say K, 5 microcoulomb charge at the 4 meter away from point P. So it's a K, first charge divided by 4, followed by second charge give you contribution to the potential at point P. So it's going to be K negative, don't forget that sign, we need that, negative 2 micro 10 to the negative 6 divided by the separation 5 meter. That's it. So once you're done with that, this is your potential at point P. So what is the amount of work done? You just take the 4 microcoulomb charge, multiply by the potential at that point. And that's it, you're done. That is the amount of energy that you have to supply to the system to drag the third charge, 4 microcoulomb, from infinity to that point P. Cool? All right. And if you get this idea and this sort of like summarize the connection between potential and potential energy, guys, this is it. Try this one. And I think this is going to look very much like the question in the exam, because what else do I need to ask you guys? It's just asking you to calculate either the potential, or once you calculated the potential, I'm just going to have to ask you, hey, what about energy if I want to drag the other charge? Okay, try this one. So in the rectangle of the figure, the sides have length 5 centimeter and 15 centimeter. Okay, very good. Q1 is 5 microcoulomb, Q2 is given 2 microcoulomb, on and on. V is 0 at infinity, so that's good. So that is your ticket to use V equal to KQ over R, knowing in your head that, okay, when you are so far away, potential is 0. So what is the electric potential at, okay, part A, the corner A. So let's do a simple task first. Let's calculate potential at point A, shall we? Well, and this is easy. So potential at A is going to be K. Now let's look at the contribution. You're going to get the contribution from Q1. You can generate sort of like, it's going to give the potential at point A to be Q1 over the distance over here. And that distance is going to be, let me put it in this SI system, 0.15. Okay. And then plus, now you look at it and John, no problem. There's a contribution from Q2 to point A. So that one will give you K Q2 over the separation over here, which is 5 centimeters. So I put it in meter. So it's 0.05. That's it. It's done. You get the potential at point A. All right. But I want to do quantitative analysis here. So I'm just going to work on the numbers a little bit. So let's work on this one. They have a common factor K. So I'm just going to drag it out. Okay, I don't want to substitute the number. You can do it at any time. It's like 9, 10 to the 9, on and on. So what you have left in here is Q1, 5 micro. Let me omit the unit here, save some space here. 0.15 plus Q2, 2 micro over 0.05. Okay, here we go. All right, I can work on this just one more. Let me multiply by, oh, sorry, it's going to be negative sign, guys. Okay, don't forget that. Okay, my bad, my bad. Here, guys. Q1 is negative. Here we go. All right, so make sure that you put the sign into it as well. So what you have over here now, I mean, I want to work out the number here. So it's -5. I multiply by 3 over 3 is +6. So it's at the end, I get positive 1 times 10 to the negative 3 over 0.15. Okay, I'm just going to leave it here. But that is the value of the potential at point A. Sounds cool?
Okay.
All right. Now, let's move on to part B, shall we? So part B is the potential at corner B, V at B. So it's going to be K. So now you look at the contribution one more time. So, okay, at point B, so Q1 will generate the potential at point B to be equal to K Q1 over the separation over here, which is 5 centimeter. Cool. All right. And then plus, I ran out of color here. Plus K. And then now you have the contribution from the Q2 to point B. Okay. All right. And that will be Q2 over the separation over here, which is 0.15. All right. Nice. Okay, simple. So what you have over here is I could pull common factor K out, and Q1 is -5 times 10 to the -3 divided by 0.05 plus Q2, 2 times 10 to the -3 over 0.15. Okay, already. Guys, 1 second here. Okay, I'm back. Sorry. Okay, so what you have over here is, all right, let me work on the number here a little bit. What is that? It's okay, -13 times 10 to the -3 over 0.15. Here we go. All right, guys, this is it. So You already got the potential at A. You got the potential at B. Now, part C is the most important one. How much work is required to move a charge Q3, the third one, from B to A along the diagonal? So you want to drag third charge Q3 from B to A diagonally. What do you think? Okay, okay. All right. I missed the sound effect. That's my part. Okay. So how much energy required to bring the third charge, Q3, from B all the way to A diagonally? So first thing first, you have to say about that, I don't care about the diagonal direction, because we already learned from last time that the potential and the concept of the potential energy and everything is path independent. So it doesn't really matter. You want to go in crazy zigzag, you want to go crazy, doesn't really matter. They're all going to require the same amounts of energy. Cool. So that's no biggie. All right. The diagonal or non-diagonal doesn't really matter. But what you care about is initial point is B, the final point is A. So you say the work required or the amount of work that you have to supply, that will give you the Q3. That's a charge that you try to move, and you move from where to where. So it's going to be the potential at initial point. So let me write it clearly like this. And, oh, I'm sorry, not initial like that. So let me put it like this first, guys. Here, let me put a delta V. Does it look good? All right. So the work done is must be equal to Q, the charge that you want to drag, times the potential difference. But the potential difference is going to be the V final minus the V initial. We learn this all the time in this course. Every time we talk about the delta, it's a final minus initial. So the final point is VA, because that's the last spot. The initial point is at B. And that's it, guys. That's all you need. You just take the VA that you calculated, plug it in here. You take the VB that you calculated, plug it in there. And that's it. That will give you the amount of the work required. And whatever you get, that will be the change in your potential energy of your system. And you are done. Got that one? Yeah. But the point that I really want to sort of like show you guys in quantitative manner over here is this. You look at this one. The VA is positive. VB is negative. So when you want to drag a charge from B to A, you think of it as like you're dragging uphill. Does that make sense? Because potential at A is positive. When you say potential is positive, you can imagine that it's elevated relative to the ground. You have a ground level and potential at A is positive. So your ground level is 0. But of course, right now the ground is at infinity, right? But at least what you say is the potential of 0 value at A is higher. And then when you talk about at B, when you look at the value of the potential at B is negative. So it's like you go underground, you go underneath the reference 0 potential. So when you want to go from B to A, so if you think about it, it's like you're dragging a charge from below the ground and you want to drag uphill all the way to A. So you can think in your head, yeah, John, at the end, you're supposed to do positive work. And that's showcased over here because you take VA minus VB. The net value of this one still give you positive. So what it means is you have to supply external work to your system to drag a charge from something underneath the reference point, whatever, below the ground, and then you drag it uphill above the ground. Does that help concluding everything that we have done so far? I guess. All right. Just to help you guys understand this thing better, I'm going to once again recall the simulation, and I think that will help a lot. So let me give you a direct link to that simulation. So give me a second here. It's a simulation at the Colorado University. So I have a direct link over here. You guys can sort of go along with me if you like. Okay, so let's try that. It's right here. So what you have here is I try to mimic the scenario that we saw just in the problem over here. Yeah. So you see that at the upper left corner, Q1, you have negative negative 5 microcoulomb, and Q2 is positive 2. So I'm going to do sort of like in scale over here. So upper left corner, I have 5, right? So let me put 5 of this negative charge there. So even though this is nanocoulomb, but in terms of the scaling, it looks good. And then I'm going to put 2 of my positive charge on the lower right corner. Cool. And in this simulation, what you can do further is this. There you go. I can check the voltage box to depict the strength of the potential. So what you can see over here, then the blue is negative, the red is positive. So when you look at this one, you can see that around the negative charge is blue. So it means the more intense blue, it means it's deeper you get underground. Cool. And the red one is the more red that you get, it means you're going above the ground. So this is like give you the like a map of the potential value. All right. But this one, it's like, okay, Ajahn, it seems like here, I have a device here that I can drag and look at the potential value here. See, at the cross hair over there, you can see that the potential is positive at the upper right corner. And if I drag this sensor here on the upper left corner, see, is negative as we calculated. So if you want to drag a charge from the lower left to the upper right, you are going uphill. So that's why you have to supply the system some energy. Does that make sense? All right. Now, it's even better sort of like visualizing this whole thing by if I would like to draw a line that representing the same value of the potential. For example, over here, I know that the potential is negative 34 something, but then I want to drag the line at every point that's sharing the same value over here. This is what you get. Bam. So that's mean on this circle over here, it's sharing the same potential. That's why they name this one equipotential line. Okay. What's the point? The point is this. If I move around and I draw that line again at a different value, so I can turn on the value by check this box as well. So I'm changing the value and then I draw it again. All right. Oop. Oh, what did I do? No. What? What? It happened once. Okay, let me do it again one quickly. Wow, it happens again. There must be some gesture that I did that give me the. Here we go. All right. So let me do it one more time here. So all right. So I'm going to draw this. Draw again. Equipotential line. There you go. And I can keep doing this everywhere, everywhere, everywhere for different value, of course. So you start seeing something here. Can you see that? So what do you see? So you start to see a contour map. Is that nice? And now I can turn on the value there. So this one is like the altitude map. When you have this to showcase like the elevation of like a mountain, something like, hey, you go above the sea level or below the sea level, on and on. So this give you a contour map. So during, on the blue side, that's the peak of the mountain. The red side, that's, think of it like an abyss going underneath the ground, okay? Down deep below ground, something like that. All right, and then when you want to go from the lower left corner, that means you go from super deep underneath the ground level and you want to drag this charge all the way to upper right corner, you are trying to climb uphill. So that's what it is. By changing the potential, you go from low potential to a higher potential. So when you want to go higher, you have to supply the energy to it to do this whole movement here. Cool? Okay. Positive higher. Yes. Wait, Ajahn, positive higher. Yes, positive higher. Oh, did I do something wrong here? Oh, my bad, my bad. Oh, shoot. I have to it's negative on the upper left. My bad, guys. Okay, thank you. It's positive on the right, right? Yeah, 2 of that here. There you go. All right, that's better. Sorry, how many do I have here? Oh, I missed one. Okay, so I put 5 here. There, 5. Here you go. All right. Thank you. Okay, my bad. Lower left is negative. Lower left is negative. There you go. Oh, shoot. I keep talking. Here we go. There you go. There you go. There you go. All right. Let me write a little bit more. More lines seems to give you a better perception of the height. There you go. All right. Very good. Okay. So lower left corner. Now I think this is correct now. Is negative. Sorry. I was just without looking at the numbers here. All right. Lower left corner is negative, and you want to drag. No, no, no. Oh, yeah, it's still here. And you still and you want to drag this charge. It doesn't have to be diagonal, right? You can drag whatever, but whatever you do, you just go uphill, uphill, uphill to the upper right corner. All right. So this one you can imagine that if you want to like you do hiking, you want to walk uphill. You're starting from somewhere below and you want to go higher in elevation. Cool. All right. So I hope this helps in terms of like give you the connections between the um, potential and potential energy. This is how you do it. All right. And the last stop, guys, there is the additional stuff that we can just put on top of this. And it looks so nice and very easy to do. Okay. And the way that you can do that is by looking at what we have already learned before. So if you look at the electric field, see? So one thing that you can see right away, it's already guaranteed. We already discussed this. We know that electric field always cut the equipotential line in the perpendicular fashion. The reason I say you already knew this because imagine the gravity. Okay, so the the bottom of the screen is lower level. If you cut this one perpendicularly, it's a downward direction. So the gravity is pointing down. And when it's pointing down, it's cut through the level. So you have the ground level, you go up 1 meter, you have another level, you go up another meter, 2 meter, you get another level. So each level, those are the same value of the potential. And when you cut this level perpendicularly, you get the gravity. Does that make sense? So the relationship between the fields and this equipotential line or surface give you the connection between the vector of the field and the surface or the line that give you the value of the same value of the potential, equipotential line. So they must be perpendicular to each other all the time. See this? See? So whenever you have the equipotential line, electric field cut through it in a perpendicular fashion all the time. See that? Isn't that cool? Yeah, cut perpendicularly, perpendicular, perpendicular. Perfect. But it turns out we can actually calculate this using calculus. We already have that tools ready. And what it is, so let me give you that right now. You won't believe it how easy it is. All right. So the reason that I want to show you that's how easy it is this. All right, this slide is kind of bad in the sense that it's a proper way of introducing this whole thing. So what I really want to do is like this. All right, let me introduce this in a very, very simple way. Okay, so go with me here in a little bit. So what I'm going to show you is I'm going to try to do some plotting. So I have, okay, sorry, X, Y, and Z. Oh, what happened here? Okay, so I have X, Y, and Z as before. So now I want a 3-dimensional because I want to do more than just 2 dimensions. So I have X here, I have Y there, and now Z is going to point to your face, perpendicular to the screen. Cool? All right, and then let's take a look at some function over here. Let's say if I have you here, it's a 2-dimensional function right now. So I have to plot it under the third axis, Z. And I want to do a simple one once again, is just X. It's X. So there's not much to it. But the whole idea is this: it's a three-dimensional plot now because we do it in a three-dimensional space. So this is still a straight line. If you want to tilt this axis, okay, let me draw it on the side over here. I hope this helps. Okay. If I compare this to, if I have X here, if I have Z here, so your Y will point into the page. You guys with me? I have a Cartesian coordinates that I can tilt around. So the one on the left, X point to your right, Y point up, so your Z pointing to your face. But if I tilt this coordinate up 90 degree, so your X pointing to your right, the Z is pointing up, so Y has to be tilted backward into the page. Cool? And this function right here, Y equal to Z, I'm sorry, Z equal to X, is just a straight line, 45 degree between Z and X. So no problem with that. But now you guys think about this. You tilt back to your left. What will you see? So imagine in three-dimensional space. All right. When you look at the right, XZ plot is a straight line 45 degree. But then if you tilt the whole coordinates back, so it's, you can think of it like, okay, Dan, I want to look along the y-axis. I mean, not y-axis, sorry. If you want to look along the z-axis, is your eyes here. You want to look downward from the z-axis, that will be your figure on the left. But what you see is you're going to see just a flat plane. So the way that I can visualize is this. So if I draw this, well, Ajahn, this is x equal to 1. It's going to be right here. X equal to 2 is going to be right there. X equal to 3 is going to be right here. X equal to 4 is going to be right here, right? So if I have these 4 dots here, dot, 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 when you tilt backward, it's going to look like this on the z axis. Point of view. So let me draw it first. Here we go. You guys with me here? So this is 1, 2, 3, 4. Cool? Nice. I don't know, make sense or not. This is a very primitive way of showing you guys. I should have like a 3-dimensional plot for you so we can tilt things around, but I'm not doing that here. I don't know why. Yeah, but I did like 3D plot when I do like calculus 4. I keep saying calculus 4. In the vector calculus, it's better for you to have a 3-dimensional plot. But anyway, I hope this is easy enough for you to see. So what you have here is when you look sideways on the right, okay, you say it's a straight line. But when you look from the z-axis down, the only thing that you can see is you're not going to see anything, but at least you know that this plane that you see from the z-axis is getting higher. So that's why I draw the line at x equal to 1 to 2 to 3 to 4, right? And here we go, guys. This is it. This is the cool stuff here. I'm going to do this. I want to do the derivative, just like what you did before. dz by dx. More than dz by dx is easy. You take the derivative of z with respect to x, you get 1. The reason is, of course, because the slope is 1. That's no big deal. Right? It's a 45-degree line. Its slope is 1. But this is the cool thing, guys. It turns out, when I say I take the derivative with respect to x, I get number 1 here. Number 1 gives me the slope. But not only that, when I do the derivative with respect to x, it's give me a clue that actually this number 1, the slope or the rate of change, right? That's the derivative. The rate of change is going to point in that x direction. Wow. Does that make sense? Why? What I'm saying is this. Here you go, guys. If I look downhill, not downhill, look down along the z-axis, I get 1 over here. It's saying that here, this is my 1 eye. 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 So what I'm saying over here is, by taking the derivative of z with respect to x, partially is a partial derivative, but in the x variable, it means I want to see what is the change of this function in the x direction. And the answer is the change, the rate of change is 1. And it's changing in the x direction. Why? Because when you go in the along the x-axis here, you're going uphill, 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 uphill. See that?
Okay.
Right? So this is it, guys. So this is the operation that we really want. What I say, what I really want is this. I can say here you go. That's my dz by dx in the I direction. And it's perpendicular, perpendicular, perpendicular. Isn't it sounds familiar here? Isn't it what I want? Yeah, well, every time that you cut through the equipotential line in the perpendicular fashion, you get a vector. And that vector is supposed to give you the fields from physics that we are doing. The only thing that's different over here is in mathematics, every time you do derivative is the rate of change. So it's a change in the positive direction because you're going uphill, uphill, uphill. But in physics, we define the field to point downhill. We point the field in the direction of lower potential, right? Gravity point down because high at the higher point you have a higher energy. Electric field do the same thing. Electric field always point from high potential to low as well. That's the concept of the potential that we need. So for physics perspective, we just want to take the negative sign of this, and that will give us the backward direction there. Cool. So when I say cool, it means so just a simple partial derivative operation along with the negative sign, slap in the directions in the direction of that variable that you take derivative with, it will give you the vector that showcase the rate of change of that function. And that's exactly what we need for our electric field from electric potential. Cool.
Okay.
All right. If you listen to me like a time, blah, 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 like what are you talking about? Don't worry. The final result is super simple. This is it, guys. So don't worry about the derivation on top, but this is what I mean. So from now on, if you have potential V as a function of space, X, Y, Z, blah, 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 what you need to do, the operation that you need is, but hey guys, take the derivative with respect to X, slap in the negative sign, that will give you the vector, which is the electric field, in that particular direction, which is X. So that's why you get the X component of the electric field. And you're done. Move on to the next one. You take the derivative with respect to y, slap in the negative sign, you will get the y component of the electric field. And then bam, you take the derivative with respect to z, slap in the negative sign, it will get, that's a z, you will give the z component of the electric field. See? So that's it. The operation is so simple. You take the potential function, take derivative with respect to the coordinates, whatever coordinates that you have, you're going to get the vector in that direction. And if you do in 3 directions, you get a complete picture of the electric field at that point, and you are done.
Okay.
So if you don't understand my explanation at all, at least you know how to do it. All right. And this operation is called gradient of a function. So it has a mathematical name for it. This is called a gradient of a function. So every time you do a gradient, then it gives you the rate of change in the directional way. So it means you get a vector out of your function. All right. I'll show you how easy it is for you to do. So if you look at the function that is given here, see, well, calculate the electric field from the electric potential that's described by the following function. Okay, Dan, it's okay. I can get the x component of the electric field by taking the negative dv by dx. That's how easy it is. And everyone knows how to do the partial derivative. Is a negative 2x y. Yeah, you treat y and z to be just constant. Y cubed, you get nothing, plus z. That's it. You already got the x component of the electric field. You keep doing it along the y, dv by dy along with the negative sign. So take derivative of this with respect to y, you get x squared plus 3y squared plus 0. Take derivative of v with respect to z to give you the electric field along the z. Whoa, that's easy. First term is gone. Second term is gone. The last term give you x. And that's it. You done.
Okay.
All right. So I hope this give you a very, very in the mathematical connections between potential and electric field in a very, very precise and quantitative way. All right. So I can do even, I mean, the question can go as complicated as you want because you have already had the electric field in your hands. So you can do anything with it. So let's do this quickly before the break here, guys. So you have electric potential. Now it's only on an XY plane. So it's down to only two variable, X and Y. And in the units vector notation, so when you say unit vector notation, it's going to be I and J, which is no big deal. I mean, I don't mind if you want to do a bracket notation, a vector notation in the matrix form, doesn't matter. All right. So in the exam, I don't think I'm going to have to, I mean, I'm not going to be exactly want this or that particular notation. Just write down. And if everyone understand the vector notation, it's fine. So what is the electric field at that particular point? 3, 2, coordinate. Marjan, no big deal. X component of the electric field is negative dV by dx. Do the derivative here. Number 2 is there. Derivative of that. Okay, let me put negative sign in the front here. 2x. That's the derivative with respect to x. Second term is gone. So it's a negative 4x. What about the y component? Negative dV by dy. Negative is there. The first term is gone. The second term is negative 3 times 2y. So it's the 6y. So the electric field vector is going to be negative 4xi with me plus 6yj. Or if you want to put it in a bracket notation, it's fine too. Or, I mean, matrix form, that's fine. Whatever you like, same thing. And now, if you want to evaluate the electric field at a particular point, so electric field at 3, 2, all you need to do is just plug in number 3 in there, number 2 in there, and that's it. You're going to get negatives 12i plus 12j, and you are done.
Okay.
Okay, so this is what I like. All right, even though you don't understand the derivation, mathematical derivation of this whole gradients or whatever that's we define in vector calculus, but in terms of the operation that we use in concepts of potential energy, and electric fields, it's easy. Negative dV by d coordinates, and you're done. All right, guys. So let's take a break right here, and I think we're done with this handout. Okay, so let's download the next one from the Google Classroom, and then we'll see each other after the break. All right, so take 10, guys. All right. All right, guys. So I got the makeup assigned in the Sky Plus system. Okay, so it's going to be Thursday at noon and Saturday at noon. All right. So if you guys can make it live, then feel free to stop by. And if not, that's okay. I think it's during the holiday, I guess. So it's right on. I will post the clip after the video after the lecture. Okay. All right. So it's already on the system. You can check the schedule there as well. Okay, guys. So now what we have left for you today is kind of fun stuff. And I'm telling you guys, I think this is the peak of the course. The reason I say it's the peak of the course because this is going to be the law that is kind of new to you. I don't think there is any mentions of this law back in the high school physics. Plus, this law seems to need vector calculus in full steam. So it's like you need the description and everything in vector format. And once you get the vector format of those definition of things that I'm going to tell you, then you still need calculus on top of that. So it's kind of like it's a vector calculus based calculation that you have to deal with this. So what we are dealing with right now is called Gauss's law. That's the one. All right. And this law, based on the concepts of flux, is going to be electric flux that you want. Once you understand this flux concepts, then Gauss's law to me is easy. Seriously.
Okay.
All right. So that's why I pay a lot of attention to the concepts of flux. And once you get that, we'll look at some applications. And the main application that we are going to use a lot is going to be a capacitor. For that capacitor to sort of like, it might look and sound complicated, but it's not. The concepts, the law, the definition, and everything is, I call it the hardest, but at the end, it seems to be the easiest in the exam. The reason is because I cannot ask you a complicated questions, because to apply this law in freshman physics level is very restricted. I don't have a lot of things to ask you. So most of the time that is going to happen is I'm going to tell you exactly what I'm going to ask in the final exam. Seriously. All right. All right. So maybe during the lecture, it's kind of like torturing a little bit. It's kind of like, oh, what is going on? But I'm pretty much like, I can guarantee that the question in the exam will be super, super, well, which word should I use? Like straightforward, because I'm going to tell you what I'm going to ask. All right. So we'll see. All right. But anyway, today's the key that I want to deliver is this one here, electric flux. That's all we need. Okay. So the concepts of electric flux actually has been mentioned already a couple of times. So the one that we did before was like when we were talking about the electric field lines. If you guys remember, we have like a figure that looks something like this before. And we mentioned, Ajan, if we talk about some area, particular area, and then everyone agree with us, agree with me, that if you look on the left, this one's supposed to be like a strong field, because the density of the electric field line is very dense, is very high. But on the other hand, if you look at this area over here, it's kind of weak field, because the electric field line are separated, it's far apart, it's not very dense. So that signify a very weak field. And now I think it's time that we are going to do this definition in a quantitative manner. How can we connect that number of lines per unit area to the electric field strength, the strength of the field? So what we really want is, hey, I want to get the magnitude, the strength of the field. And we kind of agree that it depends on the number of lines per area. The easiest way that I can define this is, well, Ajan, don't think too much. Just take it. Turn that proportional sign into an equal sign and be done with. And that's what we are going to do here. So what we are doing over here is we're going to call those number of field lines, or those electric field lines, we're going to name them flux. It's the electric flux. And we use the symbol of the phi over here, the capital phi here, to represent electric flux. Okay. And we divide it by the area. And once we have that, it's already a density of line per unit area. And we just said that is equal to the magnitude of the electric field. And we're done. All right. So we can re-express that one in terms of a product if you like. So if you want to focus on the amount of electric flux, it's going to be the products between E and A. So this one looks easy enough, Wajan. That's not too hard. So that's the concept that you can look from this figure over here, Wajan. That's fine. If you have electric field going through some area, you can calculate electric flux by taking the E multiplied by the area, right? Now the problems start to come in. If I ask you, hey guys, area is a scalar or vector quantities. It's not that big. Okay. So the thing is, you probably thought about that, well, it's supposed to be a scalar because it's just the width times the height, or the width times the length, right? But if you think carefully, if I have a piece of paper over here, it's an area, right? The width times the length is no big deal. That is fine. But then when you think about it, I can have this piece of paper oriented in this direction. It's facing up, or it can face you. It can face left, face right, face in whatever orientation that we want. So it turns out Well, we should be able to assign the orientation to an area. That's the thing. So now we are going to take the area to be a vector now.
Okay.
Isn't that exciting? Maybe not. But the reason for that is this. This figure on the right looks fine. When the electric field is going through this piece of area in the perpendicular fashion. So nobody will have any problem with this. Well, John, that's fine. I can count it. But the only problem will start to creep in. What if the electric field is actually going through this area in an angle? Are you going to count this vector to be exactly one, just like this here? Are they the same? John, probably no. Because the thing is, when we want to count the field line that actually going through the surface, we probably need some rule to count which one we're going to count, which one we're not going to count. So the very simple technique is, well, John, let's do the decomposition of a vector. So if I decompose that vector that come in an angle into two components. Yeah, I didn't draw it very well here. There you go. All right, there you go. So if I break that E, the red E that comes in an angle over here into two components, you will see that, hey, John, this is nice. The components that actually pointing in this direction is pointing perpendicular to the area. But this one that going up over here does not. So that's what we can conclude that, hey, this one not penetrating the area. You see that? The components of the electric field that is parallel to the plane of the area itself doesn't have any penetration through. So you shouldn't count this component. This component is supposed to be discarded. So you only take into account this component right here that's fall perpendicular to the field. So this is a reason why there is a this is a perpendicular symbol. That's why we call it an A perp. So we only take the product between the electric field and the area that field piercing through that area in the perpendicular fashion only. Cool?
Okay.
The concept is kind of like, okay, John, that's easy. But we will see that there are many, many cases that breaking or decomposing the electric field is sort of maybe inconvenience or might not be very intuitive. So let's take a look at the next one here. So if you have an electric field that looks already nice, it's pointing down, yeah, and then it turns out the piece of the area itself that is oriented in some angle, not in the perpendicular fashion. So look at this one, and if you want to break the electric field to be in the component that is perpendicular to the area, you can do it, of course, but it seems like it's not natural because electric field is pointing down very beautifully already. So why you want to mess with that? So why don't we turn our attention to the A and we're going to mess with the A instead? Does that make sense? So because the A is not oriented in that perpendicular fashion, so if we can define the A to be a vector, then we can do the decomposition of the area vector instead. And we're just going to take the vector of the area that indicates that this piece of the area is the part that's electric field piercing through in the perpendicular fashion only. We probably end up with the same results. Does that make sense? All right, so that's what we are trying to do. I want to do that. I want to break or I want to decompose the area vector instead of the electric field vector. And I'm going to show you they ends up at exact same result. Take a look at the next page here, guys. Okay, so how are we going to define the area vector? The way that we do it is like this. So you have a piece of paper here. So the way that we define the vector for this piece of area over here is the vector will point perpendicular to the plane of the area itself. With me? So it's mean if I have a plane of area, can you see this here? Here. So it's gonna point perpendicular to it. Okay. So you might right now you might wondering about John, why you pick this side, why don't you pick this one? Okay, that's fine. It's perfectly fine. For an open piece of area like this, you have two choices to make. You can point left or point right, doesn't matter. But the key right now is to make the vector point in the perpendicular fashion to the area itself. So take a look at this one here. So if you have electric field point from left to right, you have a piece of area that oriented in some angle with this. So the area vector is pointing in this direction here. With me, guys? Perpendicular to the area itself. Cool. So why do we define it something like this? Because it's very easy to use. When I say it's easy to use is this. So first thing first, this is what we just did. If you want to decompose the E, of course, you're just only going to take the electric field components that point perpendicular to the area, right? But now I can do equally well by having the area vector defined. I can now break the area vector and just only take the area vector that point parallel to the E. By taking just the component of the A that is parallel to the E, okay, let me draw something like this, A cosine theta. This is going to represent the area that actually perpendicular to the E itself. Does that make sense? Okay, one more time. We defined the area vector to be pointing perpendicular to the actual area. So once you get the E vector to be aligned or parallel to the area vector, is a guarantee that the electric field pointing or piercing through or penetrating the area in the perpendicular fashion. Does that make sense?
Okay.
One more time. We define the area vector to be perpendicular to the actual area itself. So if you can find the E that is already parallel to the A vector, so it's already a guarantee that that E is actually going through the A, the area, in the perpendicular direction. That's what we want. Okay, so that's why it comes down to the bottom figure over there. So instead of decompose the E, you can now decompose the A. And that decomposed area is representing just the portion of the area that is perpendicular to E. And that's it. You are
Okay.
done. But then by the time, wait a second. It looks very, very familiar here. When you decompose the E, you want the E cosine theta. And you have the piece of area A here. So the flux that you're talking about over here is, for this one, is a E cosine theta times A, right? But when you do in the bottom case, well, Ajahn, you take the A, but then you do the decompose over here, you get A cosine theta. The flux is just E times A cosine, is E times A cosine theta. See? When I say they look familiar, the reason that they look familiar because it's just the two vectors that's pointing in the same direction get multiplied. We have this kind of operation already. You guys remember something that's look very close here? Yes, you're right. Is the work is F dot S. Remember this one? And when you were calculating the work done by a force F, you say, hey, you take force multiplied by the displacement in the same direction of force. So it's an Fs cosine theta, or it's an F cosine theta S. Up to you. It depends on you want to decompose the force or you want to decompose the displacement. Same thing. So this is the reason why we love this kind of definition of the area vector, because you only want the area vector to be parallel to the electric field vector. So now I can define flux as the dot product between these two vectors, just like what we did right there. And you are
Okay.
Isn't that cool? So from now on, to calculate flux and want to write this flux calculation in a very compact form, is just take the dot product between the electric field vector E and the area vector that we just newly defined. And that's it. Do the dot product. Okay. And the way that you can represent your A vector to make it beautiful is just, okay, the A vector itself is just the area give you the magnitude. And here, n hat, remember the hat? The hat is the unit vector. The n is n means normal. So that's it. So I mean, that's perfect. We can define area vector by taking the magnitude of the area itself and you slap in the normal vector on top of that. You get a vector of that piece of area and you're done. Sounds cool?
Okay.
All right. So, why? So we're doing this for what, right? You calculate flux and now we define the area vector. We know that to calculate flux, which is just the few lines that piercing through an area in a perpendicular direction, is the same thing as doing the dot product between E and A. And then so what? So what? This is it. Imagine this, guys. All right, this is going to be so cool. Think of you have a piece of area that is closed. So when I say closed surface, yeah, so now your area is being pieces together and everything is just closed on itself. So you think of it like a balloon. So the surface of a balloon is a closed surface. So every time we talk about closed surface means you have an internal volume. Think of it that way, right? Do you have something that you enclose with? So you have an enclosed volume. And now when you look at this one, there will be no more ambiguity about which direction of the area vector that you want to pick. Because when you have a piece of paper, this is not a closed surface. It's an open surface over here. So when you want a perpendicular fashion, you still have two choices to make. It's either pointing up or pointing underneath over here, right? But once you have a closed volume like this, I mean, a closed surface like this, we can sort of like come up with an agreement. Let's say, hey, for a closed volume, the area vector is going to be defined in the outward direction only. Because now you have an inward and outward. Now we agree, let's take outward to be a positive direction, or that is the area vector that's going to point along. Cool? So with that, then if you talk about some area, for example, look at the area number 1 over there, the electric field, I'm sorry, the area vector is going to point perpendicular to it. Or maybe that's kind of big. Sorry. Huge. Okay, here we go. So the area vector is going to point perpendicular to it. If you look at the area number 2, the area vector is going to point perpendicular to it. If you look at the area number 3, the area number 3 is going to point perpendicular to it. All right. So now you know it's like, okay, wherever it is, the area vector is going to point outward, 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 outward. There you go. Everywhere, everywhere. There you go. All right. So maybe the easiest way to think of an outward direction is the hairs on your body. So if you like, let's say if all of your hairs in your body is just like straight up, that is your area vector of your body surface. That's your area vector. It's always pointing up, given that your body is a closed surface, right? Even though it's not perfectly closed, but it's enough. Okay, so that's what it is. So that's an outward direction, okay, going out. So with that in mind, now look at this scenario over here. If you have electric field piercing through from left to right. So if I want to ask you, hey guys, what is the flux going through the surface number 1? All right, so let's look at the close-up view over here. So the surface number 1, electric field is still pointing from left to right here. So the theta that it makes, the theta is still less than 90 degrees. So when you want to do the flux calculation, is going to be E dot with the piece of that area. So let me call it like a delta A because it's kind of like a tiny piece right now. But it's still E times that area times cosine something that is less than 90 degrees. So it's still positive. So we say this has a positive flux going through. The other extreme, look at the surface number 3. Right now, electric field is pointing to your right, but your area vector is pointing leftward somehow, backward a little bit. So the angle between them, theta, is now greater than 90 degrees. So when you do the dot product between the two, you are dealing with cosine theta that's going to give you a negative value, not less than zero. There you go. Yeah, cosine negative. I mean, sorry, the cosine theta that has angle larger than 90 degree will give you a negative number. So flux on this surface, number 3, will give you negative value. Whoa, it's a negative flux. And now that would be a case, of course, look at the surface number 2, that electric field and area vector are perfectly perpendicular to each other. So in this case, theta is 90 degree. So there's no flux, which makes perfect sense because when these two vectors, E and A, are perpendicular to each other, it means electric field does not penetrate the surface. Right? Make sense? It's only just glance through the surface. It doesn't have any penetration. It's not going straight through. It's not going through. So we don't count. So it's a zero flux on that surface. So in conclusion, flux through a surface could be positive, 0, or negative, depending on the direction of the field with respect to the area vector. So, but now you see what's the point of flux calculation now? So think of the electric field right now might not make a lot of sense because I mean it's kind of new and all this stuff. But if I say, if this flux representing something that's more dynamic or something that you can relate to, for example, if you think of this one as like a water stream, you have like a stream of water, water is flowing, and you represent this flowing as a flux. And you can look at this balloon is like a tank or maybe a room or maybe a container. So when you have a positive flux, it's just like a water is flowing out of this room. And you have a negative flux, mean the water is flowing in. And if you have a zero flux, mean it's not in nor out, it doesn't have anything. So if you have an inward and outward flux, and if you try to net them, you try to sum all the flux, you should be able to tell what is going to be the change in the amount of water inside the balloon or inside this container. Does that make sense? Start to have a sense of it?
Okay.
Or you might think of this flux to be like a heat flux, like there is a heat flow, and you represent or visualize that flow as a flux. So yeah, the positive flux means heat is leaving the room. You can think of this balloon as like a room. So positive flux means heat is flowing out of the room. And the negative flux means some heat is trying to enter the room. The zero flux means there's no contribution to the heat into the room. So once you net all the flux, you should be able to tell is the room is going to get hotter or cooler because you know what is going to be the net heat flow in and out. Does that help a little bit? Maybe? Yeah. So
Okay.
now for us, it's more static. It's not like a flow or anything. At least it's just a static electric field. But it is telling you something about, okay, I have electric field that actually this much of the lines is piercing out. And there's this much or this many lines is piercing in. And this much doesn't have any contribution. And eventually it's going to lead to the law that tells that out, in, and all this stuff link to what? Inside your closed surface. Doesn't that sound amazing? Okay, if not, don't worry about it right now. So let's think of just like, okay, this is like a flux calculation. I want to know how much electric field line is piercing out, how much electric field line is piercing in, given that you have an enclosed volume or you have a closed surface. Cool? Should out and in equal to each other? Not all the time. Very good question. So let's take a look at some example. All right. That's mình tiêmกันมานะ. Okay, here we go, guys. So the reason I say I just want to slap in this equation just for you to have an imagination of vector calculus approach and a little bit. So the idea is the surface that we're talking about, the closed surface, could have any weird arbitrary shape. So if you really want to calculate the net flux throughout any closed surface, you have to slice your surface into a tiny, tiny piece of area. What we did over here, the area is still big, so you call it a delta A. But now you can guess, right? Using calculus, you can slice that piece and take that piece to be super duper duper small. You can call it just a dA. And of course, when you have that dA along with the vector, okay, let me use blue for that. You have a dA for that, and then you have an electric field at that point to be E. So you can say the flux at that point is going to be meet as well. You call it the meet flux, D flux is going to be E at that point dot with the dA. So you get a feel of vector calculus now, right? And then you do it the same in the next dA. You get another tiny piece, dA, 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 dA. And each of these dA, you have E, 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 E. So you do E dot dA, E dot dA, E dot dA on each individual pieces dA. So what you have over there is just sum them up. Okay, just add them. E dot dA, add to the next one. E dot dA, add to the next one. E dot dA. But just to emphasize that everything is being done on a closed surface, you put a circle sign on top of that integral. Oh, cool. All right.
Okay.
So once you've done this, we'll give you the net flux throughout that closed surface. This is how you calculate the net flux through any closed surface using calculus, of course. All right. So that's why we call this a vector calculus right now. All right. But anyway, up to this point, don't worry about that. We're not going to try to do like super duper complicated surface that you need to do this surface integral in a crazy manner. Let's look at this one, and this will answer your question. So if a surface has a very symmetric form, like a sphere, and the electric field is just piercing out, this is very good. This is a scenario that everyone can guess, like, Ajahn, probably I have a positive charge at the center and electric field just piercing out. We already learned this from Coulomb's law. But anyway, the point right now is you have a sphere. So when you look at this one, Ajahn, that tiny piece area, dA, is going to point radially outward. At the same time, electric field also pointing outward. So no matter what you're talking about, the dA will point in the radial direction all the time. See, everywhere on the surface, dA will point out, height out. And electric field given over here is also pointing out. So right now, in this particular problem, theta is 0. E and dA always parallel to each other on the surface of this sphere. So net flux on this one supposed to be positive. You guys with me now?
Okay.
Because it's cosine 0. I mean, I can even write down as like E dA integral, and it's just E times A, let's say. All right, we'll do the detailed calculation later, next time, but not today. All right, but at least this will answer your question that there will be some surface that in and out don't need to be equal. Like this one is only out. There's no in. Electric field is piercing outward only. There's no inward flux whatsoever. So the net flux on this first one will be positive flux. Cool. All right, does that answer your question here? Okay. Now try the next one. For example, in the middle, well, it's now a cylinder. So the surface of the cylinder, you have a top surface here. You have side surface there, and you have a bottom surface here. There you go. All right. So very good. So from the look of it, Ajahn, at least I can tell you right away, flux on the side is 0 right away because electric field given over here is only going downward. So when it's only going down, there's no penetration through the side wall of this cylinder. So there's no flux through the side wall. So the only thing that you need to concern is, what about the top one? Okay, but then the top one, the surface area going to point up. That's your A. But the electric field is pointing down. So the angle between them right now is 180 degrees. It's anti-parallel. So no matter what this one give you, the flux that you get over it is going to be a negative flux. Guys with me here? But then when you look down at the bottom of this cylinder, wait, Don. At the bottom, the A vector is pointing down. Don't forget it's pointing outward. And electric field also pointing down. So over here, theta is now 0. So flux at the bottom surface is going to be positive. But from the look of this one, if the electric field looks to be very uniform and equal in value in the top surface and at the bottom surface, so whatever the flux that gets in is supposed to be the same as the one that goes out. Cool? No, that's the wrong one.
Okay.
So what you have over here is just like the influx and outflux are exactly the same. So okay. So what you have here is the net is 0. So let me call net flux. Cool. You start to get an idea of, Dan, so this is a case that we were talking about. Same thing as the one on the right. You start to be able to see it. Dan, okay, I got it. So if you have like a cube instead, you have the side wall, the top surface, the back, the front, the bottom, they all give you 0 flux. So flux on the side is 0 again. So the only thing that you need to concern yourself with calculation is just the surface on the left and the surface on the right. Cool? But now you start to get an intuitive sense. Well, Ajahn, the electric field line piercing through the left surface, that is a negative flux. This one is negative flux. And it's going to come out over here. This one will give you a positive flux. But in seems to be equal to out. How many lines are in? That is the same amount of line going out. So yeah, you can guess net flux on this one is also 0. That's sort of like an intuitive, or at least the first, sense of what is about the flux. So it's just like, okay, this is what we're trying to calculate. We want to get the net flux in or on a closed surface. Cool? All right, so that's all I need for you today. Just know how to calculate net flux. If this is good, then we're good. All right, so let's do it and see how it goes. So what I'm going to show you is, okay, let's do this one. This one is just the last one, but we do it in a quantitative way. So it's a more detailed analysis of this one. So consider a uniform electric field oriented in the x direction. Find the net electric flux through the surface of a cube h length L oriented as shown in the figure. See that? So this is more quantitative sort of setup here, but it's no big deal because you can say about Ajahn, the flux total net is going to be flux through the, let me call this surface number 1 here on the back side there. So that's number 1 there, plus the flux on the top side, flux through the bottom surface, flux through the front, flux through the back, and flux through the right surface. Let me call this surface number 2. Cool? And we just discussed, because electric field pointing along the x-axis, so it will not penetrate the top, the bottom, the front, and the back surface whatsoever. There's no penetration through these 4. So actually this can go to 0, 0, 0, and 0. Okay? So the only thing that you need to calculate is the flux 1 and flux number 2. So let's start from the number 1. So look at this surface over here. Area vector points outward all the time. It's pointing outward, outward, outward. So in this case, the area vector will point backward. Here we go. There you go. Let me put on top of that one here. So the area vector will point backward. On the other hand, if you look at the A2, the area vector will point forward like this, right? Outward, okay? So what you have for the A vector now is A, let me call this A1 vector. But the electric field is going opposite on the surface number 1. So what you have over here is the electric field is pointing in the positive x, the area A1 is pointing in the negative x. So let me do this. Flux 1 is E dot A1 vector, but E is just E. A1 is just A1, and I do cosine 180 degree. That's what the angle it makes, 180 degree with each other. So it's a negative E, and A1, then A1 is just the length times the width, L squared. And that's it, guys. You're done. Cool?
Okay.
It's a negative EL squared. It's the flux to the left surface, the surface number 1. What about the surface number 2? You're doing the same thing, is a E dot with the A2. All right, because right now the area is it's a very easy geometry, so I don't need the calculus at this point. Just put A2 right here. So A2 and electric field E are pointing parallel to each other. So the theta is 0. So it's A2 cosine 0. Cool. And the area A2 is just the length times the width is EL squared, and it's positive. So once you put phi1 and phi2 in the phi net, so that's why you get net flux is 0.
Okay.
So I get the feeling of what it's about here. Okay. All right. So that's what we're trying to get to, is to calculate net flux on a closed surface. All right. Now, one more, guys. Last one. This is more complicated one now because, all right, from the look of it, yeah, the closed surface now is in a wet shape. So let's take a look at this one. Electric field is still pretty uniform. You have a uniform electric field point horizontally, but now the closed surface is a triangular box. Okay, so what they want is, first, what is the vertical rectangular surface flux? How much flux through that vertical rectangular surface? So let's attack this one first. So this is the surface we're talking about. There you go. Well, John, this is not bad. Area vector always point outward and perpendicular to the actual area. So now the area vector for that is going to point backward. Electric field is pointing forward like this. So they're making 180 degrees with each other. So that is fine. So you say part A. Let me call this the vertical flux. So let me put a subscript V for that. It's going to be E dot with the A vertical. So A vertical is this dude right here. Cool. All right. And now you say, well, John, that's just E times A vertical cosine 180 because that's the angle that it makes between each other, 180 degrees. It's definitely going to be negative, Ajahn, because it's an inward flux. Electric field is pointing into the internal volume of this closed surface. So it's a negative E now times the magnitude of the area vector, the vertical surface area, is just this area right here. So it's just the width times the height. So the width is 0.3 meter, the height is 0.1, and that's it. You get the flux through this vertical surface. Cool?
Okay.
All right. Now try again, part B. Well, then part B, you want the slanted surface flux. This one is a little bit harder, but it's not too bad. So I think maybe the best way to think about this one is you look sideways first. Look at this. So this is side view. There you go. Electric field is pointing horizontally. Now your area vector always point perpendicular to it. That is your slanted surface area vector. Cool. So with that, that's A. Let me put S, subscript S for that. That's your slanted surface area vector. So it's going to make some angle with each other, of course, with the E now, the theta. But because the problem already gave you is this angle is 60 degree. So this is 60 degree. So from the look of it, this is supposed to be 60 degree as well. Oh, Well done. That's not bad. So that means you can calculate flux through the slanted surface to be just E dot with the A sub S vector. And it's going to be E A sub S cosine 60. Cool. Almost done. Almost done. Now, what is A sub S? A sub S is just a surface. Here, let me highlight this huge one here. There you go. That is the blue area here. That's your slanted surface area. That's your A sub S. It's going to be the width 0.3 times the length, this whole thing here. So let me call this whole length to be, what should I use? L. Okay, let me use L then. So the A sub S is just L times 0.3, right? The length times the width, right? No big deal. So that's it. Keep going. So it's going to be E 0.3 times L cosine 60. But then, should I use trigonometry to figure out the L? Yeah, probably. You probably need that. L is your hypotenuse there. But then when you look carefully on this one, wait a second. You have L cosine 60. What is L cosine 60? L cosine 60. Very good. L cosine 60 is this dude right here. L cosine 60 is just 0.1 meter, which is 10 centimeter right there. That's exactly what it is. L cosine 60 is the height of the whole triangular box over here. So now you start to see what I'm trying to get you to here. The reason for this is because here, if you look at the A sub S, and if you take just a component of this, that's what we agree. This is my A sub S cosine 60. It's going to be the components of the area vector that is pointing horizontally, right? But then we already said, whatever the area vector is pointing to, the actual area must be perpendicular to it. And that's it, guys. This AS cosine 60 is this area right here in orange over here. Does that make sense now? Maybe. Okay, I hope it makes some sense. If not, then go back and think about it a little bit. All right, we'll do more next time, of course. But for now, this is what it is. So, John, L cosine 60 is just the height. It's 0.1. Perfect. So that's why it's E 0.3 times 0.1. And now it's positive because it's, there's no negative sign come in here. And that lead you to part C. The net's entire box flux is going to be, of course, John, you have to worry about the front and the back. But when you look at the front and the back surface, nope, there's no flux through the front. There's no flux through the back. So you don't need to worry about that. So once again, the net flux is 0 because flux from part A and part B are exactly the same value, but one is negative and the other is negative. It's positive. So they sum up to 0, which makes perfect sense. Why? The electric field lines piercing in on the vertical surface, they're all going out through the slanted surface. So there's no leftover. Think of it that way. So the net flux is 0 on this closed triangular box. And you are done.
Okay.
Cool? I don't know if we call it cool or not, but that's what it is, guys, today for the flux calculation. Okay, and that is it for today's lecture. All right, I hope you learned something, and we will see each other again on Wednesday. Bye-bye.